Okay, here's the third and last quantity we need to be able to begin describing motion. This quantity is acceleration. Acceleration is the change of velocity with time. So, average acceleration is defined as change in velocity divided by time, or delta V over delta T, which means V final minus V initial over T final minus T initial for some initial and final situation. So you might notice that this definition looks a lot like our definition for velocity, where velocity was change in position divided by time. In fact, you could continue this. You could define another quantity, this change in acceleration over time. And people do that. That's actually a useful quantity. It's called the jerk. It kind of tells you how smooth your ride is if you're looking at the acceleration of a car or a rocket or something. But for our purposes, this is as far as we need to go. Acceleration is kind of the end of the line. So let's do a few examples to see how acceleration works, and then we'll talk about some subtleties that can get kind of confusing when we discuss acceleration and velocity. We'll spend quite a bit of time on this because when we start talking about the vector nature of acceleration and velocity and directions of things, it can get pretty confusing. But we'll start out with a simple example. So let's say we have a car, and this car is initially traveling at 10 meters per second. Positive 10 meters per second. So it's traveling 10 meters per second, say in the right direction or the forward direction, the positive direction. And after 5 seconds, it has speeded up so that it's now going positive 25 meters per second. Let's calculate its acceleration. So the average acceleration of this car is delta V over delta T, or V final minus V initial over T final minus T initial. That final velocity was 25 meters per second. The initial was 10. The change in time is 5 seconds. So that's 15 over 5, which gives 3 meters per second per second. Or 3 meters per second squared. So these units, meters per second squared, are sometimes confusing for people. So I want to do another example that will hopefully give you some insight as to what meters per second squared really means. So here's the next example. Let's say that a car is capable of accelerating at 5 meters per second squared, and then we'll think about what this means. So let's say it starts from rest. let's find its velocity after 1 second, 2 seconds, 3 seconds, and so on. One second, 2 seconds, etc. Okay, well let's think about what 5 meters per second squared means. I'll make a little table here. So here's velocity. Actually, let's put time over here. Here's time. And here's velocity. Seconds and meters per second. So at the beginning, when time is 0 seconds, the car is at rest. It's not moving, 0 velocity. So let's think about what this 5 meters per second squared means. 5 meters per second squared is the same as 5 meters per second per second. In other words, for every second of time that elapses, this car can increase its velocity by 5 meters per second. That means after 1 second, it can increase its velocity by 5 meters per second. After another second has elapsed, it can increase its velocity by 5 meters per second. After another second has elapsed, it can increase its velocity by 5 meters per second. So you can see the pattern. It keeps getting faster and faster by 5 meters per second every second. That's what this unit, meters per second squared, means. Let me show you a kind of the identical example with a different set of units. Let's say that this car can accelerate by 10 miles per hour per second. Now that looks like kind of a weird set of units, right? But it has the same interpretation as meters per second squared. It's saying that for every second of time that elapses, the car increases its speed by 10 miles per hour. So if we made the same table, if the car starts from rest, after 1 second, its velocity is 10. Oops. I tricked myself. This was miles per hour. After 1 second, its velocity is 10 miles per hour. After 2 seconds, its velocity has increased by another 10 miles per hour. So it's 20 miles per hour. After another second elapses, its velocity increases by another 10 miles per hour. It's traveling 30 miles per hour. So the units of acceleration are of speed per time. How much speed you get per second, or whatever unit of time you're using. Okay, a few more things to tell you about acceleration. As with velocity, there's an average version and there's an instantaneous version. So instantaneous acceleration is the acceleration's happening right now. It's not averaged over some time period. It's kind of a calculus thing. As that time interval gets really small, it's the limit of change in velocity over time. So instantaneous acceleration is how fast you're accelerating at a particular instant in time, not averaged over some longer time. Let's look at a graphical interpretation of acceleration. Remember, velocity was the slope of the position versus time graph. So acceleration is going to be the slope of the velocity versus time graph. So maybe you have a velocity versus time graph that looks like this. Well, the acceleration is this slope. That's the average acceleration over that time period. But if your velocity graph is a straight line, then this acceleration will be constant. It'll be the same value everywhere. And in physics 6, we're almost always going to be dealing with a scenario where acceleration is constant. We'll rarely see examples where acceleration depends on time, just because mathematically that's a lot easier and you don't have to do calculus. There's a special case of this graph that I want to point out. If your velocity is a constant number, if this value of velocity doesn't change, then that means that the slope is 0. And acceleration is 0. You can see that from the definition. If v does not change, then acceleration is 0. 0 acceleration means constant velocity and constant speed. Now I'm going to point out one more fact about acceleration, and we'll explore this in detail in the next video. Acceleration is a vector. Velocity is a vector. This leads to kind of a complicated relationship between these two. If I write this definition with some vector signs over these values to remind you that A and V are vectors, then it's kind of a helpful reminder. And some things to keep in mind that we'll explore in detail are that when V and A vectors point in the same direction, then your object speeds up. When V and A are in the opposite direction, the object slows down. Now, because A is a vector, negative acceleration doesn't necessarily mean you're slowing down. Remember, negative and positive signs refer to a direction that something's pointing in physics. So negative acceleration doesn't necessarily mean slowing down, it just means it's pointing in the negative direction in the coordinate system you chose. Okay, next video we'll explore that idea in more detail.